In our last video, we started talking about kinetics, and we had said kinetics talks about the rate of reactions, so how quickly reactant concentration decreases or how quickly product concentration increases. We did say that the rate varies per substance in a balanced chemical equation and depends on those coefficients, right? We looked at an example with hydrogen peroxide. So we had hydrogen peroxide and it was decomposing to produce water and oxygen. And then when we balanced it, we have a coefficient of 2 in front of hydrogen peroxide and a coefficient of 2 in front of water. So for every 2 water that I'm forming, I'm only forming 1 oxygen. Because of that, if we were to relate those rates, right, I would put a 1/2 in front of the rate of water to make it equal to the rate for oxygen, right? Because water is twice as fast, 1/2 of it is going to be equal to the rate of oxygen, right? Our rate expression had us writing my change in concentration for hydrogen peroxide over my change in time. And then because I have a coefficient of 2, right, we would put that underneath. I have a negative sign because it's disappearing, and then we would set that equal to our rate, which I didn't leave room for. That's equal to my change in water concentration. This time it's appearing, so I'm going to have a positive value. And there's also 2 of those, so I can put a 2 down below. Or you could put a 1/2 in front of it. That was equal to my change in concentration for oxygen. Remember, those brackets mean molar concentration over my change in time. Again, this one's appearing, so a positive value. I have a coefficient of 1. You can put a 1 down there if you want, but it's not necessary. So this was our rate expression, right? It's what relates the rate of the 3 different substances to each other. Again, because I have a 2 here and a 1 here, right? For every 2 water, I'm only going to form 1 oxygen. So to make their rates equal, I need to cut the 1 in half, correct? I do have a graph for us here. Let me get it up in our view where we can actually look at those rates. Let's make it a little bit bigger so everyone can see it. So my blue line here is representing my hydrogen peroxide, right? Because that's the one that's decreasing over time. I have time on my x-axis. Time is increasing from left to right. So as time is increasing, my concentration, which is my y-axis, is decreasing for hydrogen peroxide, right? As time goes on, I have less and less of it because it's reacting. The orange and the black lines are representing my products, right? At the beginning, I have none of it, right? At time 0, my concentration is 0 because it's a product. We haven't formed it yet. As time goes on, my concentration's increasing. Then the question is, well, which is water, which is oxygen? Again, remember, I'm forming 2 water for every 1 oxygen, so it's twice as fast. So this black line is representing water, and the orange line is representing oxygen. So if I look at my rates, right, the rates are different for the different substances because the coefficients are different. I do want to talk a little bit more about that, so I'm going to draw a much simpler graph where I just have 1 substance on here. And we'll make it kind of big. So time again, that's my x-axis. Concentration, again, remember those brackets mean molar concentrations. My units are molarity. That's my y-axis. If I want to look at reactants, I would start up high and go low. If I want to look at products, I start low and go up. It doesn't really matter which one we want to do. Let's look at reactant concentration. So I'm going to start somewhere up here. And then as time goes on, and then they do tend to level off a little bit. as time goes on. So as you run out of reactants, you tend to reach a state of equilibrium where it almost doesn't look like it's changing anymore. And we'll talk about equilibrium in the next chapter. When I look at rates now, I can look at rates a couple different ways. If I want to look at the rate at a particular time, so let's put a purple dot here. If I want the rate at that point, right, that would be this time. The way we would calculate that, we'll call this time 1, is I would actually take the slope of that tangent line, right? Remember, to calculate our slope, right, it's going to be rise over run, concentration over time. That is my rate, right? Concentration divided by time, change in concentration divided by change in time is my slope. That is my rate. If I wanted at one particular point, though, if I wasn't going to pick 2 points to calculate my slope, but just one, we would actually need calculus, right? Our rate would be the slope, and I'm very bad at drawing tangent lines. My rate would be the slope of that tangent line. If I wanted the time or the rate at this time, we'll use another dot here, I would take the slope of that tangent line to calculate the rate. And notice how the steepness of that purple line and that green line are different, right? I'm going to have different rates at those particular times. Those are called instantaneous rates. Instantaneous rates are going to be rates, we should just say the rate, at time t. So basically the rate at a particular time. If I, let's say my x-axis is in seconds. It could be any unit of time, but seconds tends to be more common. Let's say it's in seconds, and I wanted the rate at 30 seconds. So it would be the rate at that time. So when I say time t, whatever time it is that we're looking for. So instantaneous rate, my rate at time t, right? The rate at a specific time. And we calculate that again by taking the slope of the tangent line at that particular time period. Other rates, and what we're going to talk about more this week, are average rates. And an average rate is going to be the rate over a specific time period. So I would pick 2 points on that curve, and the rate over that time period is going to be my average rate. So my rate is going to be, I'm just going to use m for molarity. So my final molarity minus my initial molarity divided by my final time minus my initial time. Right? You would just pick 2 points. If you want to relate this to algebra, which is all it really is, x and y, right? X is my time, so I'm using t here instead of x. Y is my molarity, right? It's my concentration, so I'm using m instead of y. So all I'm doing is calculating my slope at those 2 points, right? Rise over run. So if I was to use these 2 points, right, my purple one and green one, which are now blue, I would connect to those 2 points, and the slope of that line connecting those 2 points would be my average rate. I do have an example here with an answer, which that we don't want to look at yet. So let me get that out of our way, where we actually calculate some average rates. So let me make it bigger here so you guys can see it. So I have time intervals in my first column here, right? Time 0. And this one's measured in hours, so 6 hours, 12 hours, 18 hours, and 24 hours. I have my concentration at those points. So again, this is my x, This is my y-axis. Our change in concentration is just going to be our, if we go back up here, our final minus our initial. Keep in mind here, this is my reactant, so it's disappearing. So it's getting smaller. My final is 0.50, right? If I'm looking at this box right here, we're gonna fill this in. I have 0.500, I have 1.000 initial, so 0.500 minus 1.000, right? This is M final minus M initial. I'm going to have a negative 0.500 molar. My time, I'm going to take 6. I'm going to subtract 0 from it. And I'm going to have 6.00 hours. To get my rate then, I would just divide those two. So I'm going to take 0.500 molar, we'll talk about that negative here in a minute, divide it by 6 hours, and I am grabbing my calculator here, and we're going to type this in. So 0.5 divided by 6, I get 0.0833. Watch out for sig figs here. If you guys need to review those, please do. Molar per hour. Negative sign, remember that if we're looking at our rates for reactants, forgot my delta, we do have that negative sign in front of it. So even though this value in those brackets is coming out to be a negative 0.5, I do have this negative, right? We always put negative signs in front of our reactants because they're disappearing. Our rates cannot come out to be a negative value. They have to come out to be a positive value. So that negative multiplied by that negative gives me a positive rate. So essentially you can just ignore that negative in that first column, this one right here, because at the end, I'm going to either essentially ignore it or remember that I have a negative in front of it. Basically, take-home message, rates can never be negative. If you get a negative value in this column, let's actually write this, you did it wrong. So cannot, N-O-T capitalize, be negative, right? Rates have to be positive values. It makes no sense, right? We're talking about how fast something is occurring. It can't occur at a negative speed. Let's do one more, and then I'll let you guys finish the table just for practice, and then we'll bring the answers up. So filling out our next box here, so looking at this box, I'm now going to take this value and this value. So I'm going to have 0.250 minus 0.500, so that comes out to be a negative 0.250. Remember, when you're subtracting, it is the number of digits after the decimal point. So 3 digits after the decimal point, 3 digits after the decimal point. I do want 3 digits after my decimal point in that answer. To calculate my time, I'm going to use these two. So 12.00 hours minus 6.00 hours gives me 6.00 hours again. And then to get my rate, we're going to divide those. I'm just going to ignore the negative, but if you want to do this, by all means. I do have molarity on top and hours on the bottom. I'm grabbing my calculator, so 0.25 divided by 6. And I get 0.041. I want 3 digits, 3 significant digits, 417 molar per hour for my units. And you would just keep on continuing doing that to calculate the rest of our values. So for the next boxes here, right, we would use those two and those two. So average rates, right? My rates over a particular time period. So what is my rate between 0 hours and 6 hours? This. What is my rate between 6 hours and 12 hours? This value. So those would be my average rates if we go back up here. If I want my rate at a particular time, then we actually would need to use calculus. In our next chapter, we're going to actually have integrated rate laws where all of that has been done for us and we can plug our values into an equation. But right now it's math that we're just not going to address. But I do want you to know how it would be calculated. You would take a tangent line, right? You would draw a tangent line to that point. You would calculate the slope of that to be able to calculate our instantaneous rate. I should mention our initial rate. I didn't put that on the list above. Our initial rate is really just an instantaneous rate. It's a rate at a particular time, and that particular time happens to be time 0, right? Initially, what is my rate? So the rate at time 0. So instantaneous rate, average rate, initial rate, which is an instantaneous rate just at time 0. And then calculating average rates. I'm going to show you the rest. If you feel that you need practice with this, please right now, pause the video, finish up the table, right? It's just 2 more rows you need to fill out. And then we'll hit play again. You can check your answers. So hopefully you did that. And here is the answers for the rest of the table. So the 2 that we had calculated together, and then the other 2. The units are listed above, so I know they're not here, but they're listed at the top, so you don't necessarily have to. The part that I do want to point out is notice how my rate is changing over time, right? These values that I'm putting checks next to are not the same, right? They're obviously different, and they're getting smaller, right? As time progresses, my rate is slowing down. It's getting slower and slower and slower as time goes on. And if we go back up and look at this graph, which is getting awfully messy at this point, let me erase some of it, not all that, right? Remember, as I drew it, when I got down here, it leveled off more, right? My slope up here is much steeper than my slope here, which is much steeper than my slope here. So as time goes on, my rates, right, get smaller, my reaction is proceeding slower.